We are going to do our flooding analysis based on global mapper. And first of all, I would like to explain you that there are two types of flooding that can occur on a refugee site. One type of flooding is caused by a nearby river or lake, which increase the water level, and then everything close to the lake or to the river will be flooded. And the second type of flooding is in a kind of flat area when it rains a lot and there is no proper drainage. Then just the soil doesn't manage to absorb the water, and the small stream starts to appear, and then you have a flooding on the low elevation spot. Unfortunately, this time we are going to make the flooding analysis on a situation which is not Syria, but I took an area close to my village, at my village. The reason behind is that this is a very good example because I have a river there. I have a flat area where I want to put my IDPs. And additionally, with my drone, I could do a better digital terrain model. And again, if you have a good quality digital terrain model, you have a good analysis. If you have a very bad one, you have a bad analysis. Since I am now in Switzerland and no more in Syria, the first thing that I do, I just put the right projection of Switzerland. And this, by now, you know, it's important because later on, I want to export my shape to AutoCAD to further elaborate. And the projection of Switzerland is 32 north. Now I can start to work. With my drone, with my drone, I managed to make a nice orthophoto. It's here. That's my village here. You see the quality of the orthophoto done with a drone. It's amazing compared to the quality of the freely available imagery. Okay, this is the okay, you see the difference here. Okay, now I have the free available imagery that you can have from all the world and my orthophoto picture. And with the drone as well, I did a digital terrain model. In August or September, I will also have a tutorial or a workshop how to make digital terrain model and orthophoto with drone. Here is it, the digital terrain model with my drone. What I want to say, you don't need to have a drone to have a precise digital terrain model. You can do it as well with total station. Okay, now let's do that. You can see here I have my river, where you see my mouse. This is a river that changed a lot on the quantity of the water. And I went on the field with the mayor, and the mayor told me that I can put IDPs in this area here. I just make shape so that you can see. I can put IDPs in this field. Okay, I call it field A. Okay, that's the first field. And also, he told me that I can put IDPs on this area here. This area here. I do it as well here. I do it quick because it is boring to see. Now, normally, when you go on the field and they give you a field for the IDP, and the field looks good, but it's empty, the first thing that you have to do is asking why it's empty. Normally, good land is never empty. There must be a reason. In this case, in Switzerland, because it's a farming land, but in other cases, there might be a reason behind. And actually, when I look at field A, I start to believe that maybe no one is putting the house here because I have a river very close, and maybe this river is flooding from time to time. This field. That's why no one is settling there. And that's actually the aim of this workshop, to check if this river floats or not this field. On the other one, the river probably doesn't float the field, but it is very flat. So I want to see if after heavy rain, this is going to be flooded or kind of muddy or whatever. So we are going to do two types of watershed analysis, two types of flooding analysis. First, what you have to do when you want to make a flooding analysis that flows through the river water, you have to show the computer where is the river. The software doesn't know at the moment where is the river, so you have to draw the river. We start here, we zoom in a little bit. Okay, so the river, let's say, starts here with a new line, with a new shapefile, line shapefile. I just put the river, it's here. You see, with the imagery of a drone, you really can see properly where is the water, and also it's a very recent picture, so it's real. Okay, probably almost finished. Here we have the river. Okay, up to here. Okay. River, it's a line. River, therefore I call this river line. And it's a shapefile called river line. Now I tell you why I call it river line. The thing is that the computer, I hope it's there. Yes, it's there. The computer now has the line, but it doesn't have any type of elevation on this line. For them, there is a starting point and ending point, and that's it. And now we have to give to this line an elevation. But you cannot give the elevation to a line because then you will have only 2 points. That's why you need to convert this line on a polygon. You can do it manually, but the easiest way to convert this line to a polygon is just to select the line. You select the line, okay, and then with the mouse, you go over it, you right-click on it, and advanced feature creation option, and you make a buffer. And you call it, the layer will be river buffer. It's one buffer, and the size, let's take 3 meters, for example. This is not very important. Now, if you see, I deselect, I have created a river polygon. That's good, but still this polygon doesn't have elevation. At this point, you need to give to the polygon an elevation. Once you have the elevation, you can tell the software to increase the water of 1 or 2 or 3 or 4 meters. How to do it? You need to select the digital terrain model, like that. Now I have only the digital terrain model and the polygon river. You need to select the river polygon. Now it is selected, you can see. Sorry, this is recorded. So if I am too fast, you can stop me. But as well, by the end of the day, you will have this video on YouTube. So every steps will be again visible if you look at the YouTube video. Now I have selected my polygon. I have the digital terrain model, a precise one, done with the drone. Now what I do with the mouse, I go over the river polygon and I say analyze measurement. And here you have an option, apply elevation to selected features. So now this polygon will receive the elevation from the digital terrain model. And then it will ask you from where you want to take the elevation. I take it from the terrain layers. Yes, okay. Okay. Now added elevation to the river. Now this polygon has received the elevation taken from the digital terrain model. At this point, I go back to my imagery. It can be Google Earth imagery, of course. Drone one is better, but it can be any type of imagery. And now I have to say, okay, the water of the river increase, and I want to see if my village, sorry, if my camp, field A, is going to be flooded. But now the big question is, how much shall I increase the water? 1 meter, 2 meter, or 3 meter? You cannot answer this question based on that. The only way to answer the question is going into the field and asking the farmers, the people who live there, and you ask them, when it rains, at which point do you get the water? And they will tell you, when it's raining in 1989, the water came at this point, the water came at this point. So the old people, they will have to remember where it was the biggest flooding during this very, 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 very special event. And you have to record all these points with your GPS or with your phone, and then import those points into your drawing. I went there, I asked the farmers which are living here, and they give me some points. Let me see, max level water. Where is it? Here. You see how they told me, I take out the picture, they told me, the water came up to here at this year, and the water came up to here. And if you take the picture again, okay, the water came up to here, or touched this house, and up to the end of the road almost. But be carefully, because those farmers, they know, because they were living here. But no one knows where the water came up to this point or down here, because no one was there. And it is not correct to say, okay, we increase the water of the river of 3 meters and we see what happens. Because the river might have different slope, might have different shape, and even with the same amount of water, if you have a bigger slope, the water will run faster and the water level will increase less. If the riverbed is flat, there is a less velocity of the water, but the water will increase more. If the shape of the river is more small or not flat, the river water will increase more. But if the shape of the river is very flat, there will be flooding everywhere, but the river will increase less. So it is not correct to say the river increased 3 meters all over the river. You should have as many points, such reference points, as many as possible, and then start to play with the flooding analysis. Now we have only 2 points, and I want to increase the water of this river and see how many meters I need to increase to have the water at these 2 points. So I have to activate the digital terrain model, activate it. The picture is not necessary, but I leave it. I have the 2 points. Now let's start to increase the water of the river of 1 meter. First, what you need to do is you have to select the river buffer. Select it. It's selected. And now you go to Analyze, and you can, here you have generate water level, rise or flooding. Okay, we increase the water of the river of, let's say, 2 meter level for the first time. And here you have an option, increase from selected area. That's why I have first selected the river. So now I will take, the software will take the elevation of the river and fill it with water for 2 meters and see what happens. Here you have again the resolution, like for the contour line, small number, high resolution, big number, small resolution. Let's say 1 meter resolution, and that's it. Let's go and see what happens. Might take some time if you ask a very high resolution. 1 meter should be acceptable. Let's see. Okay, you see, okay, if I increase the water of 1 meter based on this digital terrain model, I will have this situation. This area is going to be flooded, but 1 meter in this case is nothing. Let's increase for, sorry, I did a mistake. I was not putting 2 meters. I was putting 1 meter. I take it out. Okay, I save it. Okay, we do it again. Analyze, simulate water 2 meters, and here you have to write 2 meters. I forgot it. And here I do it quicker, 2 meter resolution. Okay, everything is fine. Now it is quicker because, okay, now I see I start already to have a higher flooding. But still, my points, they are not reached. One point is here, and the other point is here. So it means at that very flooding event, the river water was different. So let's increase from 1 meter more. Let's increase 3 meters. Same exercise, analyze, simulate water level rise. This time we simulate 3 meters. 3 meters. 3 meters. Tac, tac, I keep it like 1 meter resolution. Okay, let's see what happens. Okay, it looks still good, but still my flooding did not reach the very point here and not reach this point here. So what I do, I increase now 50 centimeter more. So it will be 3.5 meters, simulate water level. 3.5, which should be based on my preparation, the right elevation. 3.5. 1 meter resolution. Okay. Okay, now if I see, yes, the water arrives almost to the house here. Good. And let's see this point, almost, maybe even 4 meters, but let's keep it like that. So I can say that flooding, the very high flooding of this year, was 3.5 meters. Let's go more, let's say, on the safer way. Let's assume a 4 meter resolution, a 4 meter flooding, and let's keep this as maximal expected flooding. So that we know that more than 4 meters is unlikely to happen. 4 meters, 1 meter here, 1, 1. And we see if our field is going to be flooded or not. Now, if the field is going to be flooded by the river water, you have to go to the mayor and say, no, I'm sorry, it's impossible to put IDPs here because in case of heavy rain, they are going to be flooded. And in such type of flooding, it's very difficult to make preventive measures. You should have a big barrier, which is very costly. Normally, we don't even have money for shelter. So imagine to have money for barrier and water measure. But for sure, if I'm going to do my field here, I'm not going to put any shelter here on the lower part because this can be flooded. What does it mean? Here, it might be a playground, for example. It could be a distribution area, for example. Can be area that are going to be used during the dry season, but not for shelter, not for construction, because at one point it might be flooded and you might have trouble. But this picture doesn't look nice at all. We have to beautify a little bit. First, we have to change, we have to make it smooth. We select it and we make it smooth. Vertex editing, smooth. Okay, and we make it color. Hairstyle. We fill it with blue. We don't want a border, and we make it more transparent, like that. Doing like that, it looks kind of better. This is a picture that you can take and put it in any report and show where is the expected flooded in case of rain. I think the message is very clear how it was. In this example, I have only 2 points, but in reality, I hope, and you should have more points. You might have another point here, for example, and then you will see that if I rise for 4 meters here, maybe I don't reach that point here. So in that case, you have to split the river in sections and make different flooding analysis for every section, because this part of the section might have rise for 4 meters, but this part only 3 meters. So doing like that, splitting the river in section, we have a more realistic simulation. And how to find the right section? One good way is to look at the slope of the river. To look at the slope of the river, path profile, let's say this section, for example. Okay, it's here. Okay, from here, you see the red cross. To here, you have a slope of 4.6, 8.0, 8.1%. From here to here, 3.9. So you have to try to split the river with constant slope. So theoretically, one slope would be this one. So one part of the river could be this one. You cut the river here, and one part of the river could be this one. You see big difference on slope. This is 2.7%. You can read, I can imagine. And here it's more, 7% almost. So it means where you have 7%, most probably, you will not have such a high river water than the upper part, because here the slope is less. Okay, I think you get the message, how you can split the river. And then you have one part of the river here, one part of the river here, one part, and then based on your reference point taken from the field, you can make several flooding analysis. At the end, you combine all the flooding analysis to one single flooding analysis based on observation on the field. Okay, this is the flooding due to the river, which is this, let's say, the most dangerous one, because you can have dead people in such flooding if you don't plan properly. But you have the second type of flooding. And this is, flooding is based when you have a mainly flat area and there is no drainage, or the existing drainage is done not properly, so not properly dimensioned. Here again, you have to do the watershed analysis to understand where are the natural drain. We speak about field B now. So the watershed analysis, you know already how it works. Let's take out this one. Again, you go here, you generate watershed. Let's make a watershed analysis of 300. The size of the watershed 300. The rest looks fine. 1 meter, 1 meter, 1 meter. Okay. Now we just consider, we want to see how the field B is going to be flooded. Okay, here we have, obviously, okay, let's first start here. Obviously, the water is going to this lower part here. You might think to have a drain going like that. But the problem is here. Here, obviously, we have a main drain. Let's take out. We have a main drain here that needs to be considered, and kind of drain also going like that. At least this one has to be considered. And as far as I understand, these drains are joined both together to the river down. So now, of course, you know that you don't have to put shelter in this area. You don't have, you have to canalize somehow this water, which is not good. You have to try to canalize the water, but at least this drain has to be done properly up to this point. So what you can do now, since the digital terrain model is precise, you can start to draw your drain. Let's say one drain from here to here. And then here we are going to, sorry, we are going to dig a little bit, probably. We join here. Okay, here up to this point, to the river. It's main drain one. Okay, and we call it drain. Drain, sorry. It's a line, again, drain line. Okay, and the other is there. Sorry, I don't see if it's there. Yes, it's there. Fine. And the second one that it's important will be, okay, definitely from here to here, joining the other one. Let's take it again. From here, that's our main drain. We go straight. And we join the other one. Okay, that's called drain 2. Okay, we have now defined the location of the two big main drains. Let's see, yes, it's there. We can take out this one. Okay, these are the two main drains. Now, the good thing on that is that, why I cannot see? I do it bigger so I can see it properly. Maybe I put it 3, 4, and color black. Okay. Okay, now I can see that. Now, the good thing is that we have the exact length of the drain. If you want, you can go here and you can check all the information, the length, 470 meters exact. And here, this one, it's 340 meters. This how much? I can length 470. And this one, maybe yes, it's just, okay. But the good thing is also that we have not only the length of the drain, but we have as well the sorry, we have as well the slope of the drain. And this is one main parameter, because the slope is one of the most important parameters when it comes to dimensioning of the drain. Like I was telling you, if we have a high slope, you don't need to have a big drain, because the water speed is so big that you don't need a big drain. But if it's flat, then you need a big drain to contain all this water. And here you have a constant, you have the slope 2% from here, and then from here you have a slope 1.2%. And here you see this peak. This is a problem because there are some trees here. That's why, that's probably a tree. So we don't consider the tree, but we go up to here. And then you have the slope. And again, this is very important to know, because in next month, we are going to see how to dimension the drainage based on the quantity of rain, based on the size of the watershed, based on the type of terrain, if it's concrete, if it's forest or whatever, and based on the intensity of the rain, and of course, based on the slope. But with this software, we have already the length and the slope, but of both of them. Now, the thing is that we have also to do the watershed analysis. If you want to define the size of the drain, you need to know how much water, and you need the watershed. We did a watershed before, but you see, the watershed is limited to our digital terrain model. And it's not good, because we need a watershed which goes outside. Yeah, maybe water is coming from outside, but with this small area, we don't know. That's why we have to consider as well the digital terrain model, which is free available in internet, and we have to combine both of the terrain model. And now I will show you something interesting, and you might be surprised. This is the digital terrain model done with the drone on 3D, like that. Okay, you can see that it is. And now I just discharge, download from the internet, big size, a digital terrain model freely available, like you have seen last time, SRTM. Okay, it's here. Let's put them together. This is our precise digital terrain model, and this is the freely available digital terrain model. Now, if I look at this on 3D, you see a big problem. You see, our digital terrain model, the precise one, is kind of totally, is precise, but maybe 50 meters below the freely available digital terrain model. And of course, it's like a hole. If you do a watershed analysis like that, it is not correct. So what you have to do at this point is to change your digital terrain model in order that it match with the digital terrain model of the internet, so that you can link the both together as a unique digital terrain model. Precise one where you have the shelters, and less precise for the rest of the area. So now how to do it? You have to take 4 points. I hope you get the point. Just take 4 points. One here, for example. We call it A. And reference. I call it reference. Reference point. Point layer. A. I take another one, let's say here. E. Okay, I take one here. C. And I take one here. C, D. Okay, I have 4 points. Now I activate only one digital terrain model, and I give to these 4 points the elevation based on my drone model. So how to do? You select the 4 points. You see, they are selected now. The 4 points are selected. You go over it again, the same system, analyze measurement, apply elevation. Now you apply the elevation to those points based on the digital terrain model which is activated, so the drone one. Okay. Now the elevation has been added to the point. Now what I do, I check the elevation of the point. With this one, I go on point A. The elevation is 1,156. I just open very quick Excel. Okay, another point. This is a drone. This is drone digital terrain model. This is SRTM. This is a different. Okay, the first. Oh, sorry. Point A. The elevation was 1,156. 1,156. Okay, point B, 1,164, 1,164, point B. C, the elevation is 1,150, 1,150. And the last one, G, is 1,147. 1,147. Okay. Now I have the elevation of this 4 points based on my drone digital elevation model. I do the same exercise, but this time I will take the elevation from the freely available digital terrain model, which is this one. Okay, same exercise. You select the 4 points, it's already selected, and then go over it, analyze measurement, apply elevation. Okay, replace the previous elevation. I replace the previous one with the new one, tack, and it's done. Now again, point A, let's see the elevation 1,226. 1,226. This one, B, would be 1,238. 1,238. Habit G is 1,218. 1,218. And the last one, D, would be 1,212. 1,212. Now I make the difference. So we have 70-meter difference between my digital elevation model and the freely available digital elevation model. Now I can make the average. Average. Oops. Okay, so I see the difference between the two models is around 69.25 meters. So my drone model is 69 meters deeper than that one. Let's see it again on 3D. And here you can really see properly how big, how deep. But the relative difference is important for us, not the absolute elevation. So what I do now, I increase this full model of how much? Of 69.25. So I do like that. I go here again. I take out this one. And let me see if I remember. Yes, I think it's under option, alter elevation value, scale factor 1, offset. I think it's offset, yes. How much it was? 69.25. 69.25 meters. It should be correct. Let's see. Okay. Okay, now I've altered totally my digital elevation model. Now we can cross-check how it looks in 3D. Now, more or less, it looks, it is included in the two. You can see at this point, I can do a watershed. And no, at this point, I have to merge the two digital elevation models. What I do, I select the two digital elevation models. Now I go to, I think, yes, it's here, combine, compare terrain layers, combine elevation model, SRTM, this one, and then here the option would be cut layer out. Okay. Let's see what happens. Okay. Let me see if I take both out. Yes. This is this one. Okay, now the quality looks not so good, but it is fine. I mean, the aesthetic is not good. Now, if I take the combined one, sorry, again, including my drone digital terrain model, I have everything. And I can do now the watershed analysis, including area outside of my survey. And doing like that, I do now the watershed analysis. Generate. I will take bigger area, maybe 600 here. 600. Let's see. Let's see. Bigger 10 meter, 20 meter resolution, because the aim is to know how big are the watershed. Now maybe it's too big, 600. Sorry, let's do it again, 300. Watershed, watershed, 300. Let's see. No, it takes too much time probably. Sorry. Again. Watershed. 300, 300, but here let's take 20 meter, 20 meter. Otherwise, it takes too much time to elaborate. Okay. Let me see. Okay, I have drain. Once. No, it's too big. Still too big, the area. Sorry for that. Take away. Oops. Okay, it's there. Eh? Yes, it's there. Combine, combine. Digital model, combine, perfect. Now I do it again. Generate watershed. Of course, you have always to play around with the parameters until you have the good size. 10 meters, maybe that's the problem. 10 meters. Okay, it looks maybe better now. Why it's so deep, this area here? I cannot understand. I have a problem somewhere here with this watershed. Oh, no, that's fine, that's fine. Okay, now I have my drain and I have the watershed. Now you can see now, for example, here I have all these watershed that I will have to consider. Let's make it properly. Let's select, let's make it smooth. Sorry again. Vertex editing, smooth. Okay. Now it's smooth. Now you see better all the watershed. I have this watershed here, and this watershed here. That's good. Everything is within my perimeter, and nothing is coming from outside apparently. You see? And no, it's not true. I see here on the main drain, I have to consider as well all this water coming from this side, and this side. The watershed is much bigger, even from this side. All this water here need to be considered when I dimension this drain. And also this watershed here is very big. You see, all this has to be considered when it comes to dimensioning this drain here. Because otherwise, if you under-dimension the drain, there will be a problem. It might be too small, and then you are going to have flooding. Okay, and what does it mean? What does it mean that you are going to have flooding? And now, okay, now go back to this one, combine, go back to this one. Here we have our drain lines. We want to see what happens if you under-dimension the drain, or if you don't do anything. We just increase the water of this drain for, let's say, ½ meter, and we can see how is going to be flooded our field. We have to select again the drain. We have to convert them in polygon, advanced feature creation, buffer. This time we created in 1 meter or 50 centimeter, 0.5 centimeter. Okay, now we have created drain. No, sorry, mistake. Now I did a mistake. Sorry. Again, I select the line, I convert them in a polygon, advanced feature creation option, buffer, 0.5, but I have to put them in a new layer called drain buffer. Okay, like that. Now I have create a new layer called drain buffer. If you zoom in, you see it's a small buffer. Now, like in the river, we have to add to these lines. An elevation. We select them. We activate the digital model, and we right-click on it. Analyze. Update the measure. We have to give the elevation. Add measure attribute. Mistake again. Analyze. Okay, apply elevation to selected features. This one, sorry. Okay, from the terrain layer. Okay. Now we have added the elevation to this drain or to this soil, let's say, and let's see what happens if we float or we under-dimension the drain of, let's say, ½ meter. we do analyze. Simulate watershed. Right? This time we call it 50 centimeter, 50 centimeter, 0.5, 0.5, 1 meter, 1 meter. Okay, okay. Okay, you see, if you underdimension your drain or you do a mistake on the drain construction and it rains a lot, all this area down there is going to be flooded. What does it mean? Again, first, it means that you need to make proper drainage system, proper calculation, but as well, in order to avoid trouble, avoiding having shelters here. Because this area here might be flooded, even if you have a drainage system. And of course, along the drain also you might have some trouble. But if you manage to calculate all the watershed and the quantity of water coming in through this, it should be a problem because the calculation will lead you to have a big drain which is big enough to drain all the water into the river. And again here, what we have to do, make it nicer. First, we have 35 features, you can see. You select them all, and you make only one, combine. Advanced station option, buffer, terrain, grid, or is combined. Stop. I cannot read today. Sorry, create. There must be, here maybe on, here, combine, we combine. Now from 34, they are going to be much less. They are going to be 23. We make it smooth again. Editing, smooth. Fine with this select. With this select. Make it blue. Area style, tac. We fill it on the color blue. Okay. Don't want border. Okay, I will make it transparent. Okay. Okay, now you have the possible flooding area here due to heavy rain, and you have as well, where is it? The other one, this one. So at this point, you can show on your map where you might find trouble in case of heavy rain. Here, because of the river water, and here, in case you don't make a proper drainage system. I know it's a lot of steps, but on the other hand, I repeat, it is recorded, so you can go through and try to play again with that. For those one who don't have a global mapper, just ask me after or per email or per Skype. I will give you the link where to download a global mapper so you can exercise at home. I think it's a very easy analysis and that you can do in Gaziantep from your office, even with the digital model that you can find on internet. Of course, if you have a better one, you get better result. But I think it's a mandatory analysis that you have to do when you do a new site for IDP or refugees in general. That's my presentation. It took a little bit long, 1 hour. I'm sorry for that. If there is any question, I would be ready to answer those questions.
Thanks, Andre. That was fantastic, and really, and again, really useful. Can't emphasize enough these sort of analysis are incredibly important when it comes to, as Andre was saying, when it comes to designing the IDP settlements, refugee settlements. It's incredibly important just to understand where the water's coming from, the likelihood of flooding, the water path, and the resultant drainage. Again, let's have any questions for Andrea. Please put them in the chat or raise your hand accordingly.
I assume that some of you they are going to study it at home. Some of you maybe they give up, but thank you very much for listening.
Again, thank you. Again, thanks, Andrea, and thanks everyone for joining the presentation. As Andre mentioned towards the start of the session, these sessions are recorded. Like the previous two sessions have also been recorded. So please reach out to either Andrea or myself and we'll share the links to the YouTube presentations.